Hello everyone, welcome to Cheenta's Statistics and Data Science. So we'll be looking at two problems from the second part of CMI MSC Data Science 2019 paper. And the common theme of both these problems will be discrete math and some principles of combinatorics and especially pigeonhole principle, which I believe is a really important concept to be grasped, especially for this exam. So the first question is actually from pigeonhole principle itself. So it says that show that among any set of 7 distinct integers, there must be 2 integers whose sum or difference is divisible by 11. So just a basic recap on what PSP is. So say you have some pigeons, right, and you have some holes. So I'll just do this. And so say you have some holes, and say you have n many holes, and then there you have say n plus 1 many pigeons, and you want to fit every pigeon in a hole. So since there's one more pigeon than the number of holes, then there must be at least one hole with at least 2 pigeons. So it's basically like if you put one pigeon each in one hole, and then you have basically one pigeon extra who will have to go share a hole with another pigeon. So basically one hole has 2 pigeons. So that's how pigeonhole principle works. You kind of try to fit whatever problem you have into the small of pigeons and holes, and then you try to find out like which hole is having more than 2 pigeons. So with proceeding, it will be when proceeding in a solution of this problem, there's one more clean trick that we always use. So first of all, let numbers be A1 to A7. So remember, we are considering the sums of these numbers and the differences of these numbers. So basically, we have to show that the question says that there must be 2 integers whose sum or difference is divisible by 10. So if the difference of any 2 of these numbers is divisible by 10, then we are done, right? Because that's what it says, like we must show that it exists. So if it does, then we're done. So actually we'll assume that the difference of no 2 numbers is divisible by 10 in this case. So basically then we get that ai minus aj is not congruent to 0 mod 10 for all ij. So in order to get this very relation, we're assuming that this thing that the difference of no 2 numbers is divisible by 10. Because if it was divisible by 10, then our problem would have ended by now. So from here, we can get that ai is congruent to aj mod 10 for all I and j. Right? So this means that when divided by 10, all 7 numbers leave distinct remainders. And why is this? Let's understand why is this first. So basically, we have seen that no 2 numbers are congruent modulo 10 because we assume that no 2 numbers, the difference of no 2 numbers leave the same remainder mod 10. So what happens is that if ai is congruent to ri mod 10, and if aj is congruent to rj mod 10, then ai not congruent to aj simply implies ri is not congruent to rj, which means the remainders at the left are not the same. So when the 7 numbers are divided by 10, we basically get 7 distinct remainders. So we know that when divided by 10, there can only be these 10 many possible remainders: 0, 1, 2, all the way up till 9. So actually, we can group these 10 possible remainders in these 1, 2, 3, 4, 5, 6 sets. So what are these 6 sets basically? So there's a singleton set of 0, there's a singleton set of 5, and there's 4 pairs of 1, 9, 2, 8, 3, 7, and 4, 6. Now, just note that each of these pairs add up to 10. This is a reason why they add up to 10, and we'll be showing that very soon. So we group these 10 possible remainders into these 6 sets. So now you can see a theme, right? We have got 6 sets, and we have got 7 distinct remainders that we can get when these 7 numbers are divided by 10. Something that we have been seeing all along in pigeonhole principle, that is n holes and n plus 1 pigeons. So you can understand that there's you can kind of understand that these 6 are the holes and these 7 are the pigeons. So using pigeonhole principle, we can say that at least two of them must come from the same group. So let's see which group it belongs to. So basically, like two remainders will belong to the same group. Now, since we know that no two remainders are basically equal because the numbers are congruent, those remainders can't belong to 0 or 5. Even if they did, the sum would have been 0 or 10. So that would be congruent to 0, but they don't in this case, so we just ignore that case. So they can belong to 1, 9, 2, 8, 3, 7, 4, 6, these four pairs. So if they belong to the same group, let Ri and Rj be the remainders, where Ai is congruent to Ri and Aj is congruent to Rj. Then basically we have Ri plus Rj, which is basically these two values, either 1 or 9, whatever, any of these pairs. And this pair, the sum of this pair is congruent to 0 mod 10 because the sum is basically 10 itself. So then we get Ai plus Aj is congruent to Ri plus Rj, is congruent to 0 mod 10. So there exist two numbers whose sum becomes divisible by 10. So what we did was that we considered two branches basically. So given these 7 numbers, we considered two branches. First branch was if difference of two numbers is divisible by 10, then we're done. Right. And then we consider the alternative case. If the difference of no two numbers is divisible by 10, then we can show using PHP alternatively that sum of two numbers is divisible by 10. So this concludes the first problem. So the main takeaways from these are understanding like the goal, like if you can understand like the problem requires application of PHP, then basically you need to first arrive at what are your pigeons and what are your holes, and then try putting them in and then seeing what conclusions you can derive. And the second one would be this trick where you basically assume that is not happening and then you go along. So we move to the second problem for today. That is basically this. So we have two positive integers, n and k. The expansion of x1 plus x2 plus all the way up to plus xk whole to the power n is given as a summation of some these terms. So these are the general terms of this expression, basically given as. So there's what we call something as a multinomial, n factorial divided by n1 factorial into n2 factorial or that will nk factorial, and multiplied with x1 to the power n1, x2 to the power n2, or that will xk to the power nk. So the catch is where the sum is taken over all non-negative integers n1 nk such that the sum of these non-negative integers is n. So we have to basically compute what's the coefficient of x to the power 5 in the expansion of this this thing. So kind of we understand that this expression that we have is the general expression in this expansion. This is very similar, like, and so if you can see that if we restrict the number of terms to 2, that is if k is equal to 2, then this turns out to nothing but the binomial expansion. And in general case, it's actually called the multinomial expansion. So this is something that's very useful to know. So going along, we need to see that for this specific expression that we have, what the general term looks like. So first note that the power n, it goes to numerator like it always does. So it's 4 here, so it's 4 factorial divided by some a factorial, b factorial, c factorial, which are all non-negative integers that we have seen. They should add up to 4, and each of the terms will be raised to power a, power b, and power c. So we have 1 to the power a, which is okay, nothing. 3x whole to the power b and 2x square whole to the power c. Let's simplify this to get for this part remains same. We bring 3 out and we bring 2 out to get 3 to the power b and 2 to the power c, and we get x to the power basically b plus 2c. And we have that a plus b plus c is equal to 4. So now since we are trying to find the coefficient of x to the power 5, we know that this thing must be 5. So that's where we have this first equation, b plus 2 is equal to 5. And we know that the sum of the non-negative these integers must be 4. So we have the second equation here. So we have two equations in three variables. Common sense is that probably we won't be able to find, like, we won't be able to employ our normal techniques like simultaneous linear equations, like elimination or something like that, elimination and substitution. So in this case, we have to employ kind of some like a hit and trial method and some inspection. So the first tool that we're going to use in our inspection is basically note that they are all non-negative integers. So since they're non-negative integers, there's some nifty thing that we can derive from here after this relation. So since they're non-negative, A, B, and C are all greater than or equal to 0. But can they be like greater than 4? No, right? Like the maximum there can be is 4 in the case that the others are 0. So they're also bounded above by 4. So this gives us like a possible range of values that these three can take, which greatly reduces our searching space. So let's just get some relations out of the way. So subtracting 1 from 2, we get that C minus A is equal to 1, which is a very useful relation that we'll be using. So let's mark this as 3 actually. Now come back to this first equation, B plus 2C equal to 5. 2C is always even because 2 is multiplied with it. So B, since sum of B and 2C is 5, which is odd, B has to be odd because the sum of two evens will be even, and 5 is not even. So B has to be odd. So B has to be an odd number between 0 and 4. So how many odd numbers are between 0 and 4? 1 and 3 itself. So there we can see like we are exploiting this fact that they're non-negative integers and they're bounded below by 0 and above by 4 to get a very reduced searching space for both the values. Initially, we know that we can take any value between 0 to 4. Now we know for sure that we can take only these two values, 1 and 3. So let's just put 1 and see what happens. So we're putting B equal to 1 in this equation, in equation 1. You can see that 2C is equal to 4 and we get C is equal to 2. Trying equation 3 here, this one C minus A is equal to 1, we can get A is equal to 1. So one of the solutions is 1, 1, 2. And the next one, when we put B is equal to 3, we get 2C is equal to 2, which is basically C is equal to 1, and then we can get A is equal to 0. It's not negative, so it's allowed. So another solution is 0, 3, 1. So note that we have got three solutions of A, B, C, which satisfy both these equations. Now we wanted to find the coefficient of x to the power 5, right? So general term that contains x to the power 5 is basically this thing when you substitute the three A, B, C tuples in this. So what is the final coefficient? Since there will be basically two terms with something x to the power 5 plus something x to the power 5, the final coefficient will basically be the sum. So in this general term, we have to basically substitute these two values and then you have to take the sum. So which is this, and it turns out to be 360, which is simple calculation. So a key takeaway from this would be noting what the general expression is, like general term is, and then using the known assumptions, especially in these cases where they're integers, and using the fact that they're integers to this extent is important in this case of problems. So that would be all for today, and I'll see you in the video. Thank you.